Hello and welcome to the online Math 171 teaching lesson about complex numbers. This is section 2.3 in the text about complex numbers. Most of us first probably heard these called imaginary numbers. So this is our topic of this lesson. And let's talk about what these numbers are, first of all, how they were first encountered or imagined or discovered, however we want to think about it. Let me call up the screen of the iPad here. Okay. And complex numbers is not something, imaginary numbers is not something that people just dreamed up out of nowhere, but they were found to be necessary to solve some rather simple equations. For instance, if you had an equation like x squared plus 1 equals 0. It looks simple enough at first glance. Nothing seemingly complicated about this equation, but when we try to solve it, of course, subtracting 1 from both sides, we immediately encounter a problem that x squared has to be equal to a negative number, negative 1. And we all know that with the realm of real numbers, the numbers on the real number line, all the numbers that can actually be used, for instance, for counting things and for just basic real numbers, that if you take any two real numbers and multiply them together, we know what happens based on their signs. If they're both positive, we get a positive. If one's a positive, one's a negative, we get a negative. But if they're both negative, we also get a positive. And so it's quickly discernible that if you take any negative real number and even multiply it times itself, you still get a positive number. So it's impossible to find any real number which, when multiplied times itself, will give us a negative number. It's not difficult to find, it's impossible. They don't exist. So after actually many centuries of wrestling with this, mathematicians finally came down to agreeing, yeah, we need to deal with this situation and we need to have a new kind of number outside of the real numbers that we can use to solve problems like this. So what they came up with was to call the square root of negative 1, to call it I. It's a small letter I, and probably that's standing for imaginary is likely what that's understood to be, I for imaginary. That I was actually first used by the Swiss mathematician Euler back in the 1700s. And Gauss, the mathematician of the late 17 and first half of the 1800s, is the first one to call these numbers complex numbers. So with our equation x squared equals negative 1, we see that x has to be either positive or negative the square root of negative 1, get that right, negative 1. And now we know, well, if the square root of negative 1, if we're going to call it I, therefore, x for this equation is plus or minus our new number, I. So either I times itself will give us negative 1, let me go on to another page here. So I times I is equal to I squared, and that's negative 1. And even negative I times negative I is also I squared. So indeed, both I and negative I are solutions to the equation x squared plus 1 equals 0. So we have our new imaginary number now, I. That's the unit imaginary number. We could also have multiples of I. We can have, for instance, 2i, 17i, negative 5i, etc. In other words, we can take a real number, any real number we wish, and multiply it times I, and we get another purely imaginary number. So 2 times I is still an imaginary number. 17i is another imaginary number, etc., negative 5i. If we multiply I times 0, though, something happens here. If we multiply I times 0, something else happens. And this is nice, that complex numbers behave like real numbers in this regard, that any complex number, any imaginary number times 0 is also 0, which of course we know that's a real number. So any imaginary number, complex number times 0 equals 0. And let's consider the powers of I a little bit more here. So I we understand to be the square root of negative 1. So I to the first power is just I. I to the second power is I times I. And by definition, since I is the square root of negative 1, then I squared is negative 1. That's by the very definition of the term square root. Since we defined I as being the square root of negative 1, if you multiply the square root of negative 1 times itself, of course that's negative 1. And if we multiply I times I on the left side of the equation, that's I squared. So yes, I squared has to equal negative 1. Well, what about I to the third power? Well, fortunately, complex numbers obey powers, the rules of exponents. The rules of exponents and powers, they follow the same rules as real numbers do. And so I to the third, using the rules of exponents, is actually I squared times I to the first. By the rules of exponents, anything to the second power times that same number to the first power, you just add the exponents, 2 plus 1, so it's that number to the third power. So since I to the third equals I squared times I to the first, we've already determined how much I squared is and I to the first is. I squared is negative 1, and I to the first is just I. Therefore, I to the third power, interestingly, is just negative I. I to the third power, I times itself 3 times, is simply the negative of itself. Now there's one real number like that, negative 1. Negative 1 to the third power is also itself negative 1. What about I to the fourth? Well, I to the fourth, using the powers of rules of exponents again, is just I squared times I squared, because 2 plus 2 equals 4. So I squared, we already know, is negative 1. And so negative 1 times itself, of course, we know what that is. It's 1. So I to the fourth power actually equals the simple number 1. And let's continue this on. So what about I to the fifth? Well, no, it's not. Yeah, I to the fifth then is I to the fourth times I to the first, which is just 1 times I. And you see what happens. We're back to I to the first again. So with I to the fifth, it's simply I, the same as I to the first. And the pattern does continue. I to the sixth is I to the fourth times I squared, which is just 1 times I squared, which is just 1 times negative 1. It's negative 1. So what happens then is I to the fifth is just I to the first. It's just I. I to the sixth is the same as I to the second. It's -1. I to the seventh is I to the third. It's -I. I to the eighth is I to the fourth. It's just 1. And this continues forever, class. I to the ninth is the same as I to the fifth. It's the same as I to the first. It's just I. So it repeats every 4 integers. The pattern repeats. I to the first, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, etc. So you can tell, for instance, I to the 29th power, all you have to do is take 29 divided by 4 and see what the remainder is. Well, 29 divided by 4, 4 goes into 28 7 times with a remainder of 1. And the remainder is what counts. So it's the same as I to the first. It's just I. I to the 103rd power, we divide 103 by 4. 4 goes into 100 evenly, so many times, of course 25 times. The 25 is not really relevant. 4 goes into 100 evenly, leaving a remainder of 3. So I to the 103rd is the same as I to the third. It's just -I. All right. Now, we understand I, and we understand multiples of I. Well, finally, the world of complex numbers then consists of where we have a real part and an imaginary part added together. And this is what we call the standard form of a complex number. Standard form of a complex number is in the form a plus bi, where a and b are real numbers. Only the I is an imaginary number. And of course, b times I is imaginary. So the way we describe this, class, a plus bi is called a complex number. That term first used by Gauss in the 1800s. B times I is the purely imaginary portion of the complex number. The number A, being a real number, is the real portion of the complex number. You add the real part and the purely imaginary part, and that, yes, that's an imaginary number, but it's also called a complex number. So complex numbers can be, for instance, like 2 plus 3i, 4 minus 7i, -6 plus 2i. And we can then just have ones like 6i, which actually equals 0 plus 6i. Or you can even have -3. How is that a complex number? It turns out all the real numbers, the entire set of real numbers, is a subset of the set of complex numbers, because -3 is actually -3 plus 0i. So a and b in the expression a plus bi can, yes, they can each be 0, as well as also being any positive real number or any negative real number. So if a happens to be 0, you get a purely imaginary number like 6i. If b happens to be 0, you get a purely real number, in this case like -3. Okay. Now, most of the remainder of our time now, we're going to be talking about adding, subtracting, multiplying, and dividing complex numbers. Let's look at adding first. Let's say we wanted to add 2 plus 3i plus 5 minus 4i. How much is that going to equal? So let me get that plus sign a little better here. All right, 2 plus 3i is one complex number, and we're going to add another complex number, 5 minus 4i. So what does that turn into? Well, the nice part is we deal with the real parts and the imaginary parts separately. So we simply add the two real parts together, add the two purely imaginary parts together, and put them together in the form a plus bi, and that is our answer then to the addition problem in standard form. So we just add the 2 plus the 5 plus the 3i, and of course it's negative 4i. And so our final answer is just 2 plus 5, which is 7, and 3i minus 4i, algebraically adding the positive 3i and the negative 4i, becomes negative 1i, and just like with variables like x or y, if it's the coefficient's 1, we drop the coefficient. It's just minus I. So 2 plus 3i plus 5 minus 4i is 7 minus I. So it might suggest that adding complex numbers is not too complicated. Just keep the real parts separate from the imaginary parts, deal with each one separately, add the real parts, add the imaginary parts, keep in the signs of course, and then put them together in the form a plus bi, and you have it. So for instance, 7 minus I, a equals 7 and b equals negative 1. It's actually 7 plus negative 1i, but we write it 7 minus I. Okay. So subtracting, as you might imagine, is not complicated either. Just as when we first learned about subtracting counting numbers when we were in elementary school, the only difference is you've got the minus sign, which makes it slightly more complicated, yes, instead of adding, but it's really not seriously any more complicated. Let's pick, for instance, 5 minus 2i minus 3 minus 4i. Okay, so 5 minus 2i, that complex number, and then subtract from that 3 minus 4i. Well, we're going to do the real parts. Let's just drop the parentheses actually here. It becomes 5 minus 2i, and just as we would do in ordinary algebra, the minus sign in front of the parentheses, 3 minus 4i, we apply that minus sign to the 3 and to the negative 4i, so it becomes minus 3 minus negative 4i becomes plus 4i, and now we just combine our like terms. The 5 minus the 3 becomes the real part 2, and the two imaginary parts, negative 2i plus 4i, become plus 2i. So subtracting 3 minus 4i from 5 minus 2i will equal 2 plus 2i. So adding and subtracting complex numbers is not too complicated. Keeping the real parts and the imaginary parts separated. Now moving on to multiplying and dividing, it's a little more involved, because with multiplying and dividing, let's do multiplying first. Let's see how this is going to work. So if we did, for instance, 6 minus 5i times negative 4 plus 7i. Well, 6 minus 5i times negative 4 plus 7i, if this sort of looks like situations you've had before with variables, like 6 minus 5x times negative 4 plus 7x, or 6x minus 5y times negative 4x plus 7y, yes, we're going to follow the same procedures to solve this. Many of you have been taught the term FOIL, capital F-O-I-L, the FOIL method of multiplying like this. If you have two terms in each of two parentheses and you multiply them together, you actually have to do 4 multiplications and then add up the like terms. And that's what we're going to do here. And I'm going to write all this out on the screen. We're going to do 4 multiplications here with the firsts, outers, inners, and lasts as the FOIL method dictates. So the first number in each parentheses is the 6 times the 4. That's just a real number times a real number. And then we're going to, their next term to add to this is the 6 times the positive 7i. So 6 times 7i. And then we're going to have now the inners, so-called, the negative 5i times the negative 4, plus the last one in each parentheses, the negative 5i times positive 7i. Okay, just fit that in on that line there. So now let's do our multiplying. 6 times 4 is 24. 6 times 7i, we literally just multiply the 6 times the 7, and it becomes 42i. And negative 5i times negative 4, well, we multiply the negative 5 times negative 4, that's positive 20i. And negative 5i times 7i. We'll do the negative 5 times 7 is negative 35. And here's the catch, class. I times I. We have to deal with that. So I times I, anything times itself is itself squared. So that's negative 35i squared. And just a few minutes ago, we talked about the powers of I. And we talked about how I to the second power, I squared, is simply the real number, negative 1. So this is kind of interesting. This becomes 24 plus, let's see, the 42i and the 20i is 62i. And now we have minus 35 times I squared, which is actually negative 1. So this is actually 24 plus 62i, and then negative 35 times negative 1 is plus 35. And here we go now. Our final answer then is combining the real numbers 24 and 35, which equals 59, and taking the imaginary term 62i. That is our answer. So 6 minus 5i times negative 4 plus 7i. I don't know why we just lost this. Let me see if I can get this back here. Is 59 plus 62i. I've lost the air server. I am still writing on the iPad, but it is no longer showing on the screen. And I cannot seem to get that back once again. This has happened several times here recently. And I don't know why this is happening. Well, All right, the last two things we need to talk about then is dividing complex numbers and conjugates of complex numbers. I'm going to, since the iPad will no longer display up on the screen, I'm sorry, this is unfortunate. But since it will not, I'm going to go back to the text itself and sort of voice over the text, so to speak. In order to accomplish division of complex numbers, class, you have to understand what we mean by the conjugate of any complex number. And this is not hard, it's not complicated. The conjugate of any complex number a plus bi is simply the complex number a minus bi. All you do is change the sign in front of the I term. You do not change the sign in front of the real part, in front of the a, only in front of the bi term, so to speak. So what this means is, and I wish I could write this out and show you, but I'm not able to now. What this means is that if you had the complex number, for instance, as they have right here on the screen, the complex number 1 plus I, the conjugate of that is going to be 1 minus I. Let me show you that right here. You simply change the sign in front of the I term. That's it. Simple as that. And the conjugate of 3 minus 5i, it's going to be 3 minus negative 5i, so of course that's going to become 3 plus 5i, as they show you right here. Now, just as the conjugate of 3 minus 5i is 3 plus 5i, conjugation with complex numbers works both ways. This is sort of nice. If 3 plus 5i is the conjugate of 3 minus 5i, and it is, then it works the other way. 3 minus 5i is also the conjugate of 3 plus 5i. Conjugation is always reciprocal. It works both ways. And up here too, the conjugate of 1 plus I is 1 minus I, so therefore the conjugate of 1 minus I is 1 plus I. So the principle is, class, the conjugate of any complex number is itself. It's that complex number. So the conjugate of the conjugate of 4 plus 7i is 4 plus 7i. The conjugate of 4 plus 7i is just 4 minus 7i. And then the conjugate of 4 minus 7i returns you back to 4 plus 7i. So as was just said, the conjugate of 4 plus 7i is 4 plus 7i. So that's true with any complex number. Now, how is this useful? Turns out it's very, very useful, because the conjugate of any complex number times the complex number itself always gives us a real number. Not most of the time, all the time. Because when you multiply, you see this simple one right here in example 3, part A, 1 plus I times 1 minus I. Well, using the FOIL method, what do you get? You get 1 times 1, that's 1 squared. And you get I times negative I, which is negative I squared. But the inners and the outers, as the FOIL method calls it, 1 times negative I plus I times 1. That's just negative I plus I. It cancels out to 0. And this will always happen when you do any complex number times its conjugate. The inners and the outers, the I terms, will cancel out to 0, leaving only the real number times itself, in other words, the real part squared, and the coefficient of the I terms squared. So the coefficient of the I terms is actually 1 and negative 1, but if we just simply take the number, the absolute value of the number without the sign, just a 1, 1 times 1 is 1 squared, and that's what the product of this complex number 1 plus I times its conjugate 1 minus I becomes. It becomes 1 squared plus 1 squared, which is 2. Now, why is it going to be 2? Well, because, again, I times negative I is negative I squared. But I squared itself is negative 1. So negative of negative 1 is plus 1, and it becomes then just 1 plus 1, which is 2. And the nice part about this class is you see on the next one, 3 minus 5i times 3 plus 5i. Again, the inners and the outers cancel out, leaving only 3 squared and then subtracting 5i squared. But that 5i squared becomes 25i squared. Subtracting 25 times negative 1 is adding 25, so 9 plus 25 is 34. And here's the nice shortcut. And I'm telling you this, I'm not sure they actually show you this in the text, but it's a very nice shortcut. Very nice shortcut. If you multiply any complex number times its conjugate, the answer is just the real number, which is the sum of the squares of the coefficients of the two terms. It's the sum, it's just a squared plus b squared. So with the complex number 3 minus 5i, the a and the b are 3 and negative 5. And so 3 squared is 9, and negative 5 squared is 25. Any positive number or negative number squared is positive. So 3 squared plus 5 squared essentially is just 9 plus 25, and that's 34, which is the answer. If you did, for instance, the complex number 7 minus 4i, well, and you want to know what's that complex number 7 minus 4i times its conjugate. Well, it's going to be 7 minus 4i times 7 plus 4i. But the two coefficients are just 7 and 4. So the product of that complex number and its conjugate is just going to be 7 squared plus 4 squared. 49 plus 16 is going to be 65. And you can work that out yourself and see that that's true. 7 minus 4i times 7 plus 4i is going to boil down to just being 7 squared plus 4 squared, 65. That's a nice shortcut in multiplying any complex number times its conjugate. Now, we're going to use this principle that any complex number times its conjugate gives us a real number. We're going to use this to simplify division of complex numbers down to a form that does not have I on the bottom. So for example 4 here. And I've got to use the one in the text because the iPad is once again still unavailable. I'm checking it's still not displaying on the screen. So division problem. 2 plus 3i divided by 4 minus 2i. 2 plus 3i divided by 4 minus 2i. We're supposed to write that answer, simplify that in standard form, meaning in a form a plus bi. Some real number plus or minus some coefficient times I. Well, this is the technique class. In order to accomplish this division, what we do is multiply both the top and the bottom of the fraction by the conjugate of the denominator. It's always the conjugate of the denominator, never of the conjugate of the numerator. We multiply both the top of the fraction and the bottom of the fraction by the conjugate of the denominator. In this case, since the denominator is 4 minus 2i, the conjugate is 4 plus 2i. So multiplying the top part, which is 2 plus 3i, times 4 plus 2i, and then multiplying the denominator, 4 minus 2i times 4 plus 2i. Well, we know how that's going to work. 4 minus 2i times its own conjugate of 4 plus 2i is just going to be 4 squared plus 2 squared. It's going to be 16 plus 4. It's going to be 20, which they do come out with down below here. They do finally end up. They did it sort of the long way, but ended up with 20. I'm telling you the shortcut way is just 4 squared plus 2 squared, and that's 20. But on the numerator, unfortunately, there's no shortcut. You just have to FOIL it out, as we say. Do 4 multiplications with the 2 plus 3i times 4 plus 2i. So you have to do the 2 times the 4 and get 8, the 2 times the 2i and get 4i, 3i times the 4 and get 12i, and 3i times the 2i and get 6i squared. Now, of course, 6i squared is actually 6 times negative 1, and that translates down to the next line down here as a minus 6. So from this step class down to this step, what they've done is add the like terms 4i and 12i to get the 16i, and they've converted 6i squared into its equivalent negative 6 form as just a pure real number. So then we have 8 minus 6, combine that, is just 2 plus the 16i over 20. No longer do we have I in the denominator. It's only in the numerator. So now we can take this next to last form of 2 plus 16i over 20 and break it into its two separate parts, 2 over 20 plus 16i over 20. Well, then we've got fractions we're obligated to reduce, because the 2 over 20, of course, reduces down to 1 over 10. And the 16i over 20 is actually, you can rewrite 16i over 20 as simply 16 over 20 times I. And they don't show that step here, but I'm telling you that step. So 16 over 20 times I, 16 and 20 both being divisible by 4, we reduce the fraction down to 4 over 5i. So the final answer in standard form for complex numbers is 1/10 plus 4/5 I. That is the actual answer for how much is 2 plus 3i divided by 4 minus 2i. It is 1/10 plus 4/5 I. And you may recall from previous math courses, if you do any kind of division problem and get your answer, and of course we call that answer a quotient for a division problem, if you wish to check your answer and not just wait randomly for some time in the future when you get corrected or not of whether it's right or wrong, either corrected or confirmed, remember what you could do with a division problem. To check the answer, you can take the answer you obtain and multiply it times the divisor, and when you do that, it has to come out to equal the original number you are dividing into, the dividend so-called. And you actually can do that here to check this answer. They don't show it here in the text, but I'm telling you, you can take this 1/10 plus 4/5 I and use complex number multiplication, multiply that complex number, 1/10 plus 4/5 I, times the divisor of 4 minus 2i, and when you do that and do that correctly, you'll get the 2 plus 3i, the number we were originally dividing into. So it's a good way to check your answer. For instance, on a test or something like that where you wouldn't really be sure you got the right answer, you can do that to check your answer. So let's recap what have we talked about in this lesson. The very idea of complex numbers, so-called imaginary numbers, which is now we pretty much know that's a misnomer. We need these imaginary numbers to do real life problems in the real world. They're not just something fictitious that mathematicians created out of nothing. They are immensely useful. In fact, you probably wouldn't have your cell phones, we wouldn't have our electromagnetic radio wave transmissions and all these other things we have today without our understanding of complex numbers. So many things are invaluable for solving. But imaginary numbers came about because we needed to have some kind of number to express the square root of negative numbers. And so imaginary numbers were agreed upon as the solution, and it's a very self-consistent system now that we have this system. And we understand that we can have the imaginary number I times any real number, and it's still a pure imaginary number, whether it's 3i, 5i, 17i, whatever. And then we can even add a real number to that multiple of I, and that is still an imaginary number. It's not a real number. Even though you're adding a real number to it, it doesn't fix it. It doesn't make it real. So we call those numbers then where we have a real number plus some multiple of I. We call that a complex number. And we say that if the complex number is represented as some real number plus or minus some real number times I, then it's in the standard form A plus BI. That's a significant term, calling that standard form for A plus BI. And then we talked about adding, subtracting, multiplying, and dividing complex numbers. So I do hope this has been helpful to everybody. This is as far as we're going to go with complex numbers. It's a fascinating subject. Some of you will pursue this more in future math courses. It's a fascinating subject, but this is as far as we're going to take it in this course here. So I leave this with you, and once again, I do hope this has been helpful, and have a good rest of the day here.